In many respects, the person who's been most influential to me is the late Professor Jerry Faith, actually. Jerry was a titan in his field, without a doubt, very respected, feared by many people, and he took me under his wings pretty early on. He was actually the person who helped shepherd my promotions through. He was a casebook committee chair for both my promotions to associate with tenure and then to full. And I viewed him very much as a mentor, and I sort of emulated some of the things that I did based on the way I saw how he operated and the leadership he had in the department and the university. So I would say the late Dr. Jerry Faith, without a doubt.
When I was a graduate student, I was told one day I had to go look up a certain problem in one of Greenwood's books. And so I'm referring to Donald Greenwood, and you very quickly learn that, first of all, there's three Greenwoods, there's three dynamics books. I believe they're classical dynamics, analytical dynamics, and advanced dynamics, or principles of dynamics. Anyway, now as I'm here at the University of Michigan, I'm actually teaching a course, intermediate dynamics, and that historically was taught by Don Greenwood. And I can definitely say his books definitely influenced not only my career, but also the way I approach certain problems. Some other people are Dennis Bernstein, Dan Inman, and Pierre Kabamba. And it's actually quite amazing to have them kind of down the hall from me, because when I was, again, a graduate student, I read these papers on, robust control by Dennis Bernstein, or, quasi-linear control by Pierre Kabamba, or, something on structural dynamics by Dan Inman. And so they definitely influenced my research when I was a graduate student. They still influence me to this day, and it's really amazing to have them literally down the hall from me. So those are some people who've had an influence on me.
So I first met Pierre Kabamba as a grad student. I took his astrodynamics class. I'm not even sure if he realized who I was when I moved here as a faculty member in 2006. He has such a motivational style in the classroom. You never question that you're going to have to work hard, because you know that that's just part of being there. He has a very formal style, but it also is a style that makes you want to learn, and it makes you want to think. It's hard to take people who have not necessarily learned to think deeply and to get them to do that. And he does that not only with the students in his classes, but he also does that with his colleagues, and I very much appreciate that.
When I came here, I was not very experienced in what was going on, and Wilbur Nelson, who was chairman of the department, was very helpful. So were a number of faculty. I couldn't name them all, but they were very helpful to me. A few years later, I got involved with the dean's office. I was actually an associate dean for 14 years. And my main person there was Gordon Van Wylen, who was dean of engineering. I would say those early people influenced me most about my career here, yeah.
So I'm going to give two names because it's really hard to limit it to one. I could give a lot more, but two really important ones. Tom Adamson was the chair when I came here, and he was really key in recruiting me and getting me to come here. I had thought out of graduate school that I would go and work at NASA for a few years to get more seasoned before I started teaching, but it was really Tom that convinced me to come here because of the opportunity here. Also, during the first 5-6 years of my career, which are really crucial for any faculty member, Tom was a terrific advisor. I actually remember distinctly my doctoral advisor at MIT, Earl Merman, as I was finishing up, and he knew I was going to come here, said that if I needed advice in the department at Michigan, that Tom Adamson was a really good person to rely on. And I found that to be true. Tom had great judgment and really knew what was going on at the university and in aerospace in general. The other person obviously would be Bram van Leer. Bram and I really came in to start the CFD group here. Bram was hired about a year before I was. And Tom in the department had the vision of hiring a senior, well-established person in CFD, which Bram certainly was. He was really a huge leader in the field, and even at that time was well-established. So that first few years of Bram and me designing the CFD curriculum and getting a research program going and getting it funded was, a huge part of my career, and Bram played a just really key role in that.
The person that influenced me the most was a fellow by the name of Larry Rauch, who joined the faculty a year before I came. He's long since retired. As a matter of fact, he's deceased, but he was quick to give me responsibility and was my conscience in terms of what I'd be teaching and that type of things.
I would say that I really could not single out a sort of one person, but when I joined here, I would have to single out Professor Bill Anderson. He was really a person that I could go to and talk to because he had a broad view of aerospace engineering because he had worked in industry and he himself had a company. He was also doing a lot of academic research, so he always stressed the balance between doing work that was academic as well as doing work that would have some impact in industry. But if there's a group of people, I would say it's the students. I think we get the really strong undergraduate students who really keep you excited about your own topic and also asks questions that are very piercing and makes you think in new ways about problems. So I think that has been a major influence in my career here at Michigan.
Well, that is hard, but the person I worked very closely with, and he was my advisor in many cases, was Dick Morrison, years ahead of me, and he was my boss here, and he went to Florida to work at Cape Canaveral for a while, and I went with him as sort of an assistant, and so I had an interesting year at Cape Canaveral for about 15 months, and then we came back and I went on working in the lab. He always had the ability to make you feel like you were important and what you had to say was important, and but he was always interested, not just doing it because you had to. So that was worthwhile.
Well, it's a long story. A faculty member from here who's now deceased, Harm Buning, came and spoke at the high school physics class I was teaching. He had just created or just spent the last few years of his career creating the landing control system for the lunar lander. And he talked about that, and I at that point thought Michigan Aerospace was the best thing there was. And it just took me a long time to get here. I think that had a big influence on me. Since I've been here, the faculty as a whole has had a big influence on me. It's a really great group of people doing some really great things.
The first person that influenced me the most was Professor Lesher, because at the time Professor Lesher was looking for students to help him construct the Teal, which I wound up doing in the basement of East Engineering with my little Cleco pliers. That was all he'd let me touch. And the next person was probably Professor Harm Buning, because in the year when we had to decide what our concentration was going to be, I had the good fortune of meeting him, and then he became my advisor, which turned out to be a really outstanding event in my life, because I think it really changed my life, because it taught me a number of things about education and how you can shape your education when you're here. He had the opinion that if you have an idea and if it makes sense as part of your curriculum, then go make it happen. And then finally, I can't leave out Roger Glass, which is why we're here. This is the wind tunnel where so many things happen for students, and did so much in the 60s, because this is what was one of the facilities that allowed you to experiment and to make things happen with hardware. And Roger Glass, again, was a perfect person for that, for working with students, because he mentored us, he helped us to understand what was required, and was not only a good instructor, but also a good friend.
My favorite professor was Professor Tom Adamson. He became kind of my mentor when I had him in aerospace engineering. He really helped me grow as a student. He helped me learn a lot of what I needed to know to help my future. So it kind of took me under his wing.
People like Larry Rauch, William Root, in particular, gave me a lot of guidance. They were senior members of the department at that time. Also Bob Howe, who was later a department chair, and a very close personal friend and colleague, Elmer Gilbert, who has who is in the same general field that I am in, so he's had a strong influence on my own work and my own development. In more recent years, since say the 1990s and to today, I've had a number of good friends in the flight dynamics control group, Dennis Bernstein, Pierre Kabamba, and others, and including Ilya Komanovsky, who was one of my former PhD students, and I'm pleased to say is a member of the department today.
One is Roger Glass. Roger was my supervisor at the time. He was a research scientist. He graduated from U of M Aerospace. And he was from, I guess you would say, from the old school. He was a super gentleman, and he was extremely intelligent, and he knew how to handle people, and he knew how to work with people, and he knew how to work with technicians. And I've always strived to be just like Roger in a lot of cases. A lot of times when you're under stress, I think about Roger and how he would have handled it, and that made a big difference in my career here at U of M. The other person, of course, would be my dad, Leo. He was a technician here in the aerospace engineering department back in the 60s and the 70s. Unfortunately, he passed away in 1979. One of the little surprises they had for me when I started working here is my first day, my office was my dad's old office over in the old building, and that was quite a pleasant surprise. All his equipment was still there in his office, all of his books with his name on it and his handwriting. Between Roger and my dad, Leo, I believe that's what influenced my life mostly to continue on a good, honest work ethic here at the university.
Well, I've been working on this particular topic that is right here, namely unblade control of noise and vibration in helicopters. I started working on that before I came to the University of Michigan. However, that research matured to the extent that it could now be flown on a helicopter like this one. And it was demonstrated that whatever the calculations predicted in terms of noise and vibration reduction have been actually verified in the flight test. For me, that's very exciting to think of something and then see it on a helicopter flying. Not everybody lives to see such a thing. And actually, as I said many times, I hope that before I die, I see it on a production helicopter. I even said when I gave the Nikolsky lecture that I refuse to die until I see it on a production helicopter.
I really like education, and I'm very proud of educating students here at Michigan. So I would say one of the things that I really have a lot of pride about in terms of things I've done is educating PhD students. My students now are faculty members, including here at the University of Michigan and elsewhere. And other students are actually people who are working at NASA, the Air Force, think tanks, et cetera, doing really interesting work. And I find that to be exciting. In terms of my own research areas, I think there are two things that stand out. One is the role that our lab played on a couple of space missions called DS-1 and Dawn, which are NASA missions, robotic missions exploring the solar system. We were on a team that helped develop the ion propulsion units that are flying those spacecraft. That's kind of exciting. And the other has been the whole notion of taking technology that 2 decades ago was really led by Russian scientists and engineers. And now, because of the work we've done over the past 2 decades, one could argue that now the United States has the lead in terms of advanced space propulsion technology. So I would say those are the things that I sort of look back on my 2 decades here at Michigan and think, okay, maybe we made a difference.
So one of the most significant things that I have had the privilege to be involved and actually to lead was the revitalization of our PhD program. We have every student in the first year now virtually funded from university departmental resources. And none of them are involved in teaching activities during that first year. The teaching assistant opportunities, however, come at later years, typically when they are already PhD candidates. We encourage that experience. However, we like them to be more mature, which benefits them for the experience as well as benefit our undergraduate students by learning and interacting with more mature professionals. We have what used to be a world-class program to be one of, if not the best graduate programs in its areas in our nation, which were educating and graduating the future faculty members, government and industry researchers, and leaders in both the government and private sectors.
So I'm going to go back to when I was a graduate student in the 1990s. My PhD was actually in computer science, but pretty soon after I started the program, I realized that I loved things that flew. So I need to have some kind of hands-on experience with flight vehicles. At the time, the department was just beginning to think about unmanned aircraft, otherwise known as model aircraft or drones. And so I was part of a group of graduate students that spent long days and nights kind of as an extracurricular design, build, fly type activity, building model aircraft for research purposes. And so that really made a big influence on me. It made me realize how much I enjoyed hands-on experiments, how much I really needed to do things involving flight as opposed to moving bits and bytes around in computers. And I've been doing it ever since. At this point, I guess I'm known as a bit of an outspoken advocate of freedom for flight of these drones or unmanned aircraft, and it's made a difference in my research, but also I think academia has a real need to stand up and say, this is important to our field. It always has been ever since the Wright brothers flew model aircraft, and we need to keep going.
After I'd been here about 6 or 7 years, I was looking for new problems to work on and started talking to Tomas Gambosi in the Space Sciences Department in the Space Physics Research Laboratory. And we realized that the codes that were being used to model space weather at that time, or to look at coronal mass ejections and other solar events, were really behind the time on a couple fronts. And we wanted to bring to the table really modern computational techniques like solution adaptive techniques, which I had worked on, Godunov schemes, which both Tomas and I had worked on, and massively parallel computing, which I was fairly new to, but was a little bit ahead of what was going on in the field at that time. So Tomas Gambosi and Quentin Stout and I formed the Center for Space Environment Modeling, and working with some really outstanding research scientists like Gabor Toth and Igor Sokolov and Bart Vanderholst and Darren DeZeo, really built up a code base for the space weather modeling framework, which really now is one of the leading ways to model space weather. So that's another accomplishment I'm really proud of.
The thing that I got started with was a program called the Guided Missiles Training Program. It's a program that started a year before I came and was very instrumental in improving the department and getting it set up for the future requirements. And that's paid off because I could see where the things that we learned in that and what we achieved are being followed even today. And that would be concentration on the area of control systems and things associated with control and space vehicles and that sort of thing.
Actually, there were three things. Okay. Number one was taking Professor Ed Lesher's flight instrumentation and flight dynamics class, where we actually got up in the U of M Cessna 182 and did test flights, and that was a really fun, educational part of my Michigan experience. Learned flight dynamics, and so getting a hands-on feel was really important. The second one was when we were able to take a University of Michigan Aerospace Engineering sponsored bus trip to the Kennedy Space Center to see the launch of Apollo 14. It was an incredible trip from the day we started. We were lucky, we were able to get there and there wasn't a launch scrub, and we were able to see a terrific launch of Apollo 14. We could actually see the shock wave coming at us through the mist, and it was just an amazing thing to watch. This enormous vehicle would produce this quite large shock wave coming at us, And when it got to us, of course, you could feel it. And so that was a really special part of our experience. And then the third significant event for me was taking Harm Buning's AERO 483 class, and that was our senior design class. Our group designed and basically developed Project Medusa, which was the Michigan educational satellite for Alaska. It was good for us. It was a great learning experience. And we presented, of course, Project Medusa to industry leaders who had come to see our presentation. That was a really great experience.
When I came here, there were hardly any experimental facilities in the structures area. So when I was recruited, Professor Tom Adamson, who was the chair, and Joe Isley, the senior faculty member in structures, basically wanted to see that the structures experimental aspects were solidified. So I started what today is called the Composite Structures Lab, and there were many others who followed, like Professor Pete Washaba, John Shaw. They're all experimentalists who were added on. So the single most thing I would say from my own perspective is, really running this lab and making it really a top-notch laboratory for research in composite structures, which, as we know today, is a contemporary topic. Future aircraft platforms will be made with composite structures. So I am glad that I had that opportunity to do that.
I don't really have one thing. We did some work with airbags. That was worthwhile. They were just beginning to come out, and the university has the unit that's involved with automobile safety. So somebody there asked us to do some testing on airbags, and that was interesting. My first reaction is there's no way an airbag could open fast enough to do any good, and so we ran some nice tests, took pictures with a high-speed camera to see how fast the bag would deploy, and we're talking milliseconds, and it does work, if it works.
For me, the whole thing started when I came to the University of Michigan at a party in the first year that I was here, where I met Professor Thomas Gombosi. We were talking about fluid dynamics in the heliosphere, and he said, I would like to model these processes with a method that I've heard of that is very good. It's called Godunov's method. Do you know about that? And then I answered him with saying, you're standing in front of the world's expert on Godunov's method. And that's how our collaboration started. And we worked for a few years on ionospheric problems, and eventually this grew into the space weather modeling effort, which also used Godunov-type methods of the kind that I've been involved in developing.
There are two things that I did that I think while I was chairman. One is that I hired 13 people during my stint as a chairman, and I was given great support by the dean's office because they supported me in getting not only junior faculty but senior. And to show that, we went from 0 to 3 very top flight people, and it was only because I was supported by the dean I could get senior people, Brom and Phil Rowe, and also Ken Powell. We had so many people retiring at one time that they didn't dare hire everybody at the same age, because then in another 10 years they'd all start going again, so we had to sort of spread them out. Oh, and there was another thing that I think I was happy with, and that is working with the FXB Association. They came and offered to give some money toward the building, and I helped with that. In fact, I think I helped get about $10 million in that, and the engineering department gave $4 million, so we got the $14 million we needed. This used to be another building that was right here, and then there was a parking lot behind. And they started off by putting in the laboratory first, and then they moved everybody from this building into the laboratory, and then they knocked this building down, then finished this building and attached it to the FXB building. That was a lot of work, but it was worth it. And I really enjoyed working with the Association François-Xavier Bonnieu in getting all these things done. The building, I worked with the architect and with the person that worked from the company. We had our differences as we were going along, because I'd say, I think we ought to do this differently, and the guy from the building say would, maybe we shouldn't. But later on, you know, he paid me back. So they found out which office I was going to go into. And they said, come here, Tom, I want to show you something. I went in there and the whole office was pink. And he said, you know, that's the first time I've ever seen you unable to speak. But it was very funny that they got back at me with that.
Well, a real interesting thing happened being at the University of Michigan. We were working on these small energy harvesting devices. And my postdoc at the time decided that we could use that to run a pacemaker, as well as the sensors that we're looking at for the Air Force. So he wrote a paper on that, and then somebody from the medical school saw it, called us up, and we started working on this project to create self-powered pacemakers. And I think that's fairly significant.
We were very much involved in the building of the FXB building. Tom Adamson, who was the chairman before me, had been instrumental with many others in raising the funds and developing the idea for the new building. We had been in, of course, the building nearby, the old AERO building, and it was totally unsuitable for our needs at that time. And during that period which I was the department chairman, I spent really a good part of my time working on both the planning for the building, working with the architects and then eventually the builders on the building, and making many, many decisions about carpeting and furniture and tile, you know, the color of walls, and so many things that is involved in the construction of such a large project. I had not had prior experience in that area, so I learned quickly. But then in 1994, we finally moved into the new building. We had, I remember, many celebrations that we had with both dignitaries from the college and the university, as well as from the state of Michigan, alumni and friends of the department. So it was a great fun time to celebrate the new building and to celebrate the department as well. My part in the FXB construction project was one of the highlights of my career in terms of the impact on the department.
I think what's changed the most has been the integration of more laboratory experiences for our undergraduate students, and an increased level of research activity in the faculty. The importance of students coming out of our program and having a laboratory experience gives them really a total system look at an aerospace system. A lot of educational programs produce students who have sort of compartmentalized information in their mind about aerospace. So they might know the fluids part, they might know the propulsion part, they might know the structure part. But because of our laboratory sequence, they see how it fits together as a system. And this is really valued by the companies who hire our students.
We went from slide rules and analog computers back in my day, that's all we had, not even personal calculators, to now a world of digital processing, computer design, CAD/CAM, we have computer-aided graphics. It's changed a lot in that regard for engineering analyses and engineering design. But in a lot of ways, the University of Michigan Aerospace program still has the finest professors, the best students in the country come here, and we have a very dynamic and diverse student body. And so that's still here, and that's a big part of why I love Michigan and why I came to the University of Michigan in the first place.
Well, I think there's more of a concern about research now than there was back when I first joined. We have a little bit more emphasis in the areas of control than we did when I first started. Of course, we have nicer facilities here on the North Campus than we had on the main campus when I first joined the faculty. Those are the things, several things that occur to me.
The thing that comes to mind most is the ability of students to build very capable devices and very capable vehicles. When I started a couple of decades ago, many of the design projects we had with our students were paper-based design because we just didn't have the technology to have students build meaningful vehicles. But now, because of miniaturization of power sources and miniaturization of computer systems, advanced programming, advanced propulsion systems, and control systems, we're actually able not only have the students design things, but actually build things and test things. The fact that our students can use quad rotors, for example, to build vehicles, they can do remote control blimps, and in many cases our students are actually building spacecraft that not only operate in space, but to collect data that people are very interested in is very exciting.
Well, I came in '56. '57 was Sputnik. That was the start of the space program. And the whole tenor of the department changed to be not only aeronautical engineering, but space as well. And eventually it became the aerospace department, you know. That was a big change in the focus of the department and our thinking about it. I was in structural engineering. And in 1956, there was a paper written about what became known as the finite element method. It was a way of converting differential equations into a set of linear algebraic equations. It introduced a whole new way of solving problems, but it required a computer because the linear equations included lots and lots of equations. So the space came and a whole new way of solving differential equations appeared on the scene. And, well, the whole world changed, you know.
These big grants completely changed the kind of way we do business because we started collaborating and writing papers together. But then what really made another huge difference was Wei Shi, who joined us in 2005. He was an extraordinarily dynamic and competent chair. And he did many things, including instituting major changes in the graduate program. The way we ran our PhD exam was completely revamped under his leadership. And then he was the most successful department chair I've ever seen in terms of recruitment. When he joined us, he got 3 new positions from the dean to recruit new faculty. And with 3 new positions, he recruited 9 new faculty. And everybody thought that this is a miracle. How can you do that? But he did it. And then Dan joined us in 2011. And he's an equally or maybe even more dynamic chair. And we continued prospering and recruiting people. So fortunately, the period I was in, the last 15 years, were the period when the department really prospered and did very well and went up in rankings, and everything was positive.
One of them is the great increase on student-led projects, team projects. I think the creation of the Wilson Center has facilitated a lot of the implementation of this project. We have had the opportunity to get an environment where the students can learn from each other, can learn from technicians, as well as have space to develop their projects. We have projects on both atmospheric flight as well as space flight. And they encompass a lot of things beyond even what we teach in the classroom that involves payload integration and communications, systems engineering in general, as well as aspects in finance, scheduling, different things that has to go along with a project. So they have the opportunity to really apply things they learn in the classroom in a practical project, even before leaving the university. So I think that's something that has grown tremendously in this last several years.
So when I started the program was heavily oriented towards engineering science, which is really looking at fundamental issues in aerospace engineering. But that has shifted more towards a vehicle-oriented focus, as well as a focus that has elevated the space engineering side of things more, to make it more visible. So there's a better balance now. I think our department is more balanced than when I joined, because it was more focused on engineering science, and I think it's for the better of for the department and for the future.
When I first got here, they were lucky if they had 100 students, and the class size was 15. And if we have 30, they changed it into 2 parts to have 2 sections of the class. And you don't see that anymore. In fact, later on when I was a chairman, I had one graduate class where I had 50 or 45 or 50 people in it. So that's a big change that happened throughout the years. And I remember the first class I taught, it was a 2-hour class in kinetic theory. And I was sort of nervous, and I went through enough material in one class to last a week. And I'm sure the poor students out there broke their pencils trying to keep up with me.
Well, I've seen a lot of changes. I guess I would say that students now get a lot more involved in hands-on projects. When I started, everybody pretty much learned out of books, and now people work on the solar car, they work on the jet engine club and build jet engines, they work with UAVs and fly little things around, you know. And so I think the students get a lot more involved in projects, they get more motivated and more excited now. And I think we're trying harder to keep up that activity rather than just focus on the book work. Now what we see is we have cooperative programs with China, programs with the rest of the world. The Boeing 787 was built in 60 different countries and then assembled in one place, you know. So I mean, the aerospace industry is multinational, and we had a recent graduate come back from General Electric. They said, you know, why are you selling all our technology to the Chinese? And so he said, well, that's exactly what General Electric wants to do. We first consider them to be customers, and then they become collaborators, and then eventually they become competitors. But he thought that was a good idea because that makes GE better and makes the aerospace industry better. So we're not looking at the rest of the world as being our enemies or our competitors, but they're really collaborators and use their skills and talents to advance the aerospace industry.
What has changed dramatically is the amount of work that certain people do now. There's so much more of it. We're now taking care of facilities such as the FXB building. We're taking care of what we call the PEPO lab, Plasma Electric Propulsion Lab over in Green Road. And we also took in the new satellite dish that's over off of North Territorial Road. So our jobs as technicians has expanded tremendously. We no longer just work on laboratory experiments. We now are responsible for the facility itself, the infrastructure of the facility. The amount of work is just tremendous, but we enjoy it every day, every minute.
This department has always had a very strong basis in engineering science, and it has shunned the trendy and the fashionable, and always tried to stick to basics, make sure that those are never compromised. And when you go out on a limb, that's fine, but the limb has to have the prospect of becoming a mature, thick branch, as thick as the trunk itself. And I like that, and I think it's still this way. When I came here, for instance, I was hired to start teaching and research program in computational fluid dynamics. That was sort of a trendy thing at that time, but it was also predictably something that would be enormously important in the future. And Professor Adamson, who was the chair at that time, I'm talking about 1985, was so wise as to hire two people, a senior and a junior person, myself and then Ken Powell, who is now rather senior himself. So that was sort of going out on a limb and doing the trendy thing, but it was very well founded. Whatever you do, make sure that you do not do it because someone else is doing it, but because you can very thoroughly, profoundly motivate it.
Much has changed. In 1967, that was the period in which the space program was at its height, and the University of Michigan was very much in the center of that activity. Today, the world is a very different place in many ways, certainly in terms of the changes in the technology. But the subject matter has changed. The kinds of courses we taught, although in many ways have similar titles. If you looked in the undergraduate bulletin, you would find that the courses at that time and the courses now superficially are very similar. We talked about the courses in the same areas of gas dynamics and aerodynamics and propulsion. But the details of what is covered there, both in terms of the teaching function as well as in terms of the research that people were doing, has changed enormously. Another change that has happened is in the students. People often ask me, were students different in 1967 than they are today? And that's a very difficult thing to answer, and people have different perspectives on that. My own sense is that students have changed in many ways. They come with different kind of preparation, different kinds of backgrounds, different kinds of interests then versus now. It used to be the case that many students came in engineering with backgrounds having worked on farms with agricultural equipment, or having worked on ham radios and built their own simple electronic kits, or in some cases having worked on their own automotive vehicle. And so those are the kinds of experiences that they had in those days. And those were very important, mostly mechanical skills, mechanical experiences, but they brought that. They now have the capability for building and testing their own designs and their own vehicles, flight vehicles. And that's relatively easy to do using various kinds of components and systems that are available and easily put together by students. It used to be quite impossible to do this in the past in engineering education. And I think aerospace engineering particularly benefits greatly from having students involved in a whole range of mathematical modeling, engineering science, and engineering test capabilities, and they get exposed to that throughout their academic career. And I think that's actually a real plus for today's students.
Well, I think there are two things. One, I think that's really important is whom we hire as faculty members. And I think in general we've been doing well at this, and particularly lately. We went through a period in the department when I was here maybe 10 years ago, 15 years ago, up to 10 years ago, where we had sort of a hiatus on hiring, partly because of economics and partly just because of uncertainty and so on. And I think that wasn't particularly healthy for the department, but right after that, in particular one way she started, we got some more spots and we hired several really outstanding people. And that helped both energize the department with some young people and some people in new fields like unmanned air vehicles and small satellites. And it also helped us diversify the demographics of the department, both in terms of age, and also we had not had a woman faculty in the department since my arrival. We had Pauline Sherman on the faculty. She retired right before I came, and we went nearly 20 years without a woman on the faculty. So when we were able to hire Anouk Gerard and Ella Atkins, that was the start really of diversifying the department in that respect. The other thing I'd say is we need to pay attention to the curriculum, and this is something where I think we have not done as well of late. Michigan's known as a department with a strong curriculum that puts out people with a really good basis in the fundamentals and also a good sense of relevant information in aerospace. I think we have strong individual faculty members doing good things in the classroom, but it's been a good 15 years since we've looked overall, particularly at the undergraduate curriculum, to see how things fit together, if there are gaps, if there are things that we need to add that have not been in the curriculum up till now. So I'm hoping that over the next 2 years, that's something we do to kind of revitalize that and keep the undergrad curriculum in particular vibrant.
First of all, keep doing some of the things that are done right now really well. I've always been very impressed with how the faculty take such pride in teaching fundamentals in their subject area, and they encourage students to think as opposed to just solve the problems and get through the problem sets. And then there's really an emphasis in excellence in student teams as well as in the classroom. Not only be incredibly successful in student competitions for things like design, build, and fly, but in a couple of cases there also have been some really good successes in the students going out and starting their own companies, which hopefully eventually Ann Arbor will be known for unmanned air vehicles and so on, as well as cars and other things.
MIT is bigger, Georgia Tech is bigger. Some of the other departments, such as Caltech and Stanford, are different. They don't have undergraduate programs, they are strictly graduate, so it's difficult to compare. But for us to continue thriving, we have to be able to go up to 30 faculty and maybe a little bit more, because then we will be competitive with everybody else who is in the top 3, okay? The other ones I'm not worried about. Related to this is to hire really bright, young, active faculty who have the potential to become superstars in various areas. And it's difficult to predict which areas you want to pursue. The biggest mistake any department can make is to simply try to emulate what other departments who are your competition are doing, because by doing the same things that other people are doing, you may be missing the boat. You really have to identify what is best for our particular combination of talents that we have.
I guess my main statement would be keep up what you're doing, it's fine. I've really been impressed with how the department has been conducted and what it's achieved since I retired.
It's funny because I was in theory most of the time I was here, but I would say they need more experimentalists. So much is done now with computers and in computer, computational fluid dynamics and everything. And I think what they need are more people in experimental work, more practical work, because I think that is more helpful to the students, at least to get more of it than they have now. So I think that would be a big change that would be good to hire some people in experimental work. I think Jim Driscoll would be very happy to hear that.
Well, the first thing is I've noticed that students really like these hands-on projects. They like experimental work. They like to do things and build things. And because the computer is so popular, I think a lot of professors are doing projects with computers, teaching classes out of computers. We can't forget about the experimental side of what we do, because that's what the students want. We also need to look at some of the new advances like cleaner fuels, less pollution, maybe solar power for some applications. You know, really interesting new ideas in aerospace. We need to diversify into those areas.
Well, we need to continue to go after the best and brightest and most diverse student body, go after the students that are motivated, but also have high ethical and moral standards. That's really important when you get out in industry, and especially aerospace, to have a very, very, very moral and ethical standard when you're out dealing with spacecraft and rockets and manned space flight. You have to have that as part of your soul.
This is a program that was the first of its kind in our nation. And it has since been leading the engineering, education, research and service. We need to continue building upon this and foster a lifelong learning environment a vibrant research and an active service within our program. In connection with support to the College of Engineering, I believe we should look for new ways of exploring education, both in and outside the classroom. And we've been doing a lot of those. And examples are the flipped classroom, and technology that we are embracing to enhance our ways of teaching. Now, in parallel to that, it's also critical that we keep a vibrant research environment in our department. We have addressed that, and we have continued to address that through bringing faculty members and outstanding students. But we are facing significant challenges on the funding side of the equation. The traditional funding sources that we have had, namely the federal government, is been decreasing its investment, and it's expected to be a shift between the federally funded sources to more private funded sources. Those are things that would impact significantly the aerospace community due to the historical nature of our funding support, not only for the academic environment, but as well as industry, that we've been heavily dependent on government funding. So those challenges would have to be addressed so we can keep that vibrant environment for our future students and faculty members.
Coincidentally, we just happen to have with me a report that we're filing with the department that involves the input from the entire Industry Advisory Board just to answer that very question. What is it that the department can do to continue to maintain this razor edge of fine-tuning that we do in the department? We're encouraging students to get more information, to understand more about the work that goes in, not only to the individual components. The components are in and of themselves are very important, but when you think of how all of this has to work together as a system, the structures, the aerodynamics, the noise, and so forth, all works together to make this product viable. And so we need to do more of that. The reason we're saying that is we think that's going to make our students more competitive in the future as they approach industry. The second big part that we've seen in unanimous agreement among the board is the influence that the products have on the environment and on the ecosystems that they're influencing. Sustainability is another consideration. How does this product influence sustainability over the life cycle of its product? Its reuse, its ability to influence the materials that it takes. Our planet doesn't have an infinite supply of a lot of materials, so we need to be creative in how we do that. We think the students here can do an excellent job, as they've demonstrated time and time again, and consider these tweaks that are being made in the spirit of continuous improvement. Because knowing what I know now, I think that our students are going to be second to none in the future, and I think it speaks well for the department and for the future of our program.
Our plan is to go forward with this sort of dual emphasis on the basic science of aerospace engineering and having his hands-on fly, build, design approach. So we'll continue to go in that direction. We'll continue to have an involvement with our Industrial Advisory Board. We'll continue to have professors who actually are driving the aerospace profession and its future by being on national boards and committees. And those are the things that we can do as a department to be part of the future.
Being an aerospace engineer has been pretty amazing. How I got into it is kind of funny. I was in mechanical engineering actually as an undergraduate student, and my friend Andre said, James, you have to go into aerospace engineering. You know, it's really challenging, really fun, and you just got to do it. And so I started poking around looking at grad schools that had aerospace departments, and I thought, yeah, like this stuff's pretty interesting. And I have to say, it's been like the time of my life. I've been able to work on really interesting problems, a variety of different problems, from, you know, Martian rovers to flexible spacecraft. And I've been able to go to NASA centers and give talks and meet very interesting people all throughout the world. And it's been very fulfilling, not only professionally in the sense that I worked on really interesting problems, but I've been able to meet like really interesting people who are also really excited. And it's just been, for lack of better words, just a blast. which no pun intended, but it has been a blast. I didn't even mean to say a blast, by the way. I didn't even mean to do that.
People always ask me, how did I end up in aeronautical work, you know? I grew up on a farm in Ohio, you know. As a little kid, I liked airplanes, and when the opportunity came for college, I thought, well, engineering sounds good. Why not do aero? It was just seemed the thing to do. Well, it's been an exciting time. I've had a lot of great students, you know. I don't know how many hundreds of thousands of students over 42 years of teaching. I came here, there was no space program, but the very first year I was here, I had 2 students in my class who became the Gemini 4 capsule, Ed White and Jim McDivitt. I didn't know they were going to be astronauts, you know. And then later on, I had 2 other students that became rather famous in Apollo 15, Jim Irwin and Al Warden. Now, those are the famous ones because they've done famous things. But I have a lot of other students that I can't begin to name them all. If I go much further, I'll be leaving out some of them, you know.
I would say that aerospace engineering has really been the defining field for me as a person. So when I came here, I got to be honest, I was more excited about, you know, doing research here and then eventually maybe even going to NASA to work for them. But then what kept me here was the fact that I had this opportunity to work with young people. And so really a team environment, and I suddenly realized I really enjoy teaching, I enjoy working with young people, I enjoyed going to the lab and working with them, alongside them. And so off of that energy, I think I like to think of myself as somebody who is now well regarded in the composite structures area. So that helped me to diversify my interests, not only in aerospace, but in other areas like applications in automotive engineering, marine engineering, because there is a movement towards making things lighter, but still maintaining what we call structural integrity. And that has propelled my interest as well as my name in the aerospace circles as somebody who sort of, you know, goes a professional in the field of aerospace structures. So that has been very rewarding to me, and I owe it to the department.
Aerospace engineering has been a haven for me. I started out as an astronomer. I studied astronomy up to my PhD, but as a doctoral student, I got interested in and involved in computational fluid dynamics. I found astronomy too narrow. I went through a few years of teaching numerical analysis at Delft University of Technology, and finally found, as I said, my haven in aerospace engineering. You might say, well, that's only one application, aerospace engineering. Isn't that as restrictive as astronomy? No, it isn't. In the first place, aerospace engineering requires very high accuracy. And that's what I was after, to get computational methods that are very efficient. That is, they can get results that are very accurate in a limited computational time. Also, I found that it was quite possible to work in the aerospace engineering department within the College of Engineering, and to have contacts and collaboration with people from a variety, 5, 6 other departments without impunity, which is much harder to do as an astronomer. And finally, I would say that I like being in the engineering environment better than being in the science environment. I just like working with engineers better than with scientists.
This has been pretty much my career for the last 30 years, working for the AERO department. I actually came here to the department visiting with my dad when I was just a kid in high school, or even younger than that sometimes. And I remember going to see the moon rover that was running on the track over by the Green Road facility that we have now. And that really inspired me to continue on to want to work here at the U of M. So I went to school, got a degree in digital technology, and I was able to get a job here as an electronics technician. When I began working here early in '84, putting in long hours was your career. You worked many, many hours. A lot of the research experiments required just timeless effort and persistence and pursuit of solving the problem. I was married in '82, and then I had my 2 daughters, and they pretty much spent quite a bit of time here in the AERO department. I still remember when my 1 daughters, I brought them here for Bring Your Kids to Work Day. And one of the professors came down to my office and he goes, "Do you know who that is that's in the elevator?" And I says, "It could possibly be my kids." And he says, "They're charging people to ride the elevator up to the 3rd floor." And I go, "Yeah, that's probably my kids." But the department has always been part of my life. It's not just a job, it's not just a career, it actually becomes part of your life.
My transition from the University of Michigan to Ford Motor Company took place in 1969 and 70. And one of my opportunities was to try to continue to make contact with the University of Michigan Aerospace Engineering Department, even though I was with Ford. What it allowed me to do is to remain in contact with the faculty who were here, who were Professor Buning and then Professor Lesher, as I mentioned. It gave you the confidence and the experience then to make some ties, not only to help out the company, but to explore your own interests. And one of my interests at the time was sailing. And at the time, the America's Cup, which is sailed on the east and west coast, was a major program, but the only sponsorship was for marketing and sales. So I worked with another team and convinced them that they needed to do more science on the design of the sails and hull to make it structurally sound as well as lightweight and have improved aerodynamics. Well, that's the same kind of thing we were working on at Ford. And so my training at Michigan gave me the experience to understand the language of those structures and of aerodynamics so that I could go to my management and explain to them why it's important to be involved with the sailboats. I think that's what my training at Michigan did for me, is it gave you the basic exposure plus the confidence and the awareness of what it takes to get other projects done. And all along, though, staying involved with the AERO department so that the expertise that I knew was on campus could be brought to help projects succeed at Ford.
An education from Michigan is special in the first place, but getting a Michigan engineering degree opened so many doors for me. It seemed like every time in my professional life when I needed a door opened, my Michigan education and my Michigan engineering degree opened that door. It allowed me to go and do things that I'm not sure I could have done with any other education, with any other university. People respect and admire Michigan graduates, and industry knows what they need and what they're looking for, and Michigan students provide that for a great number of employers. That was the biggest thing for me, was getting a Michigan degree made my career.